Oh, today we'll first review the notion of filtered phi modulus or filtered Dieudonné modulus or filtered isocrystals. So let's start with the following definition. We fix a vector space. Say, okay, so let K be a vector space. We will denote first by Filk K the category of filtered K vector spaces. K, oh, sorry. Yeah. Filtered K vector spaces. So, namely, the objects delta equipped with decreasing filtration which is exhaustive and separated. Okay. And morphisms in this category, so as a natural, it's a natural thing. So you have two filtered vector spaces, delta prime and delta second. So a morphism is a linear map which preserves the filtration. The point is that this is an additive category. With kernels and co-kernels. Which is not abelian. So if we have an object of this category, delta, we can consider the graduated filtration, graduation of this filtration. And consider the following quantity, Tn of delta, which already appeared in the Udi's talk of in this morning in the context of crystals. So this is a sum following sum. Sorry. Yeah, this is H. H for Hodge. And this assignment is additive. So if you have an exact sequence, Then Hodge of delta is Hodge of delta prime plus Hodge delta second. And also we can remark that Hodge can be computed in terms of determinant of delta. So if we denote by the determinant of delta the higher exterior power of delta, so this is a one-dimensional vector space with induced filtration, one-step filtration, and again, sorry? Finite dimensional, yeah. Thank you. So then Hodge coincides with Hodge of the determinant. So now let's consider, yeah, thank you. A field K0, which for a moment is completely different, so this is a different picture, which is a field of fractions of with vectors with coefficients in a perfect field of characteristic P. Yeah. This is infinite filtration in both directions, but it is exhaustive and complete, so almost all quotients are zero. So you have only a finite number of terms. Yes. Yes. Yes, but this is one-step filtration, yeah? But it is somewhere, it is exactly, so the only break is at TH of delta. This is an exercise, so, so for example, if you take two copies of K, so consider K included by K, this is delta 0, this is delta 1. Here you take 0. Take K. So this is your, say, delta 1, 0, delta 1, 1. So you can find easily the kernel and co-kernel, but the sequence will not be exact. So of this map, so in categorical sense, yeah. So the kernel is clearly 0 because we have your identity here. Co-kernel is also 0. Okay, so let's consider Frobenius acting, absolute Frobenius acting on K0. So today, for us, a phi module over K0 is by definition a finitely dimensional vector space. M with a semilinear isomorphism F, which is semilinear with respect to phi. So we denote by M K0 phi the category of phi modulus. And here there is no problem. This is an abelian category. Even tensor category. And in this category, we define Tn n for Newton. The following way. So this is the p-adic evaluation of lambda, where lambda is defined as follows. We take the determinant of M, which is also a one-dimensional K0 space with an action phi. So we take a basis here, and phi of E is lambda E, and the evaluation doesn't depend on the choice of E. So we have a similar property, so this assignment is additive. These examples fit in a general picture. So let me just summarize that. Here we have two assignments, important assignments. The rank of a filtered module, which is just its dimension, and we'll call degree a function th. So here we have a well-defined rank, which is a dimension of M over K0. And we define the degree of M as minus Tn of M. So minus this choice is a little bit technical, but yeah. In this case, it is compatible with the choice so adapted in, for example, in the book of Fontaine-Fargue. And the both examples, so there is a third example which will be important for real applications to Fontaine-Fargue curve. And also, so in fact, this is the first example where this phenomenon were maybe probably studied. So the category of vector bundles over a projective curve, where so the rank of a vector bundle is well defined, and so its degree is defined as the degree of its determinant. So in all these cases, one can define the slope function. So in all cases, one defines the slope function as the degree of x divided by the rank. And we have a formalism of slopes. So harder Narasimhan filtration. Which was generalized in the framework of very general categories by Yves. So slope filtrations, a paper which is published. So where André formalizes this, so the theory of harder Narasimhan. So he supposes that some not necessarily abelian category is given. So we have an additive category. With kernels and co-kernels. We have some, so the class of short exact sequence. We have these two functions, additive functions. Degree and rank, which satisfies some list of properties in particular, so there should be, the rank should be positive. So they both take values in Z, but in addition, the rank should be positive. And yes, some more conditions. Which explain why the theory works not necessarily for abelian categories, but also in some larger categories. And so in this situation, one defines the slope of an object X as a degree by the rank. We say that a monomorphism F in this category is strict if it sits in a short exact sequence for some z. So if X is the kernel of some morphism from Y to Z. Yes, so yes, yeah, this is, I mean that the formalism of André is more general, but yes, but the case of exact categories corresponds perfectly to this picture. Yeah. And one says that X, maybe Y is semi-stable. If only if for any strict f from X to Y, mu of X is small. Sorry? Yes, the monomorphism F is, because it is strict, it is monomorph. We have this inequality. And the theorem of Narasimha generalized by André, but it seems the proof follows the same steps. There are more theoretical category problems. States that for any object X in C, there exists a unique filtration X. Such that the inclusion of, sorry, it's X, of X I to Xi minus 1 are strict. And that the sequence of slopes is strictly decreasing. Yes. Yes, yeah. Okay, yeah, okay. Six, yeah, okay. So, filtered modules. So in this case, M is strict. So this category is abelian. M is strict if and only if it is a clinic. The success, yes. Sorry. Thank you. In this case, strict objects correspond exactly to isoclinic objects. And we have the theorem of Dieudonné-Manin already. Semi-stable, yeah. Theorem of Dieudonné-Manin. Which says that for any M, there exists a unique decomposition of M into the direct sum of isoclinic modulus. So the slope of M is exactly minus slope of M in the sense of Dieudonné-Manin theory. And yes, so any subobject of an isoclinic object has the same slope, yeah. So the definition. And over an algebraically closed any module decomposes uniquely in a direct sum of isoclinic modulus. Yes, for different slopes. Yes, okay, yeah, but so over an algebraically closed K, isoclinic modulus of slope, say lambda equal to A by B, are exactly the direct sums of copies of K0 phi quotient by phi B minus PA. So one can also remark that if M is of slope 0, so this is equivalent to the existence of an OK0 lattice in M, stable under the action of Frobenius, and therefore the slope 0 modulus corresponds exactly to a Tal modulus in the sense of first talk. Yes, isoclinic, yes. That they are stable, so phi induces a map from a lattice to itself. No, because you have a non-zero slope. If, for example, phi is a division by p, the image, yes, yes, yeah. Oh, definition. So a filtered phi module over a finite extension k of k0 is by definition a filtered phi module M equipped with a filtration structure. Yes, plus, filtration structure on Mk, which is the extension of scalars from K0 to K. So on this category, we define the degree as the degree in the sense of Hodge theory, so filtered structure, THM, plus minus the Tn of M. This is a definition. Okay, Mk. And the rank is always a dimension of M. Okay. Oh. Definition. M is weakly admissible. If and only if it is semi-stable of slope 0. So concretely, this means that Th of M is equal to Tn of M, and that for any subobject n of M, strict, Th of n is less or equal to Tn of n. So this is a Fontaine definition of weak admissibility, but written in terms of harder Narasimhan formalism. So the following result is very easy to prove, but it is surprising. So the category MF of weak, so of weakly admissible filtered phi modulus is abelian. But the proof is easy. Next paragraph, hierarchy of p-adic representations. Sorry? This one? The category of weakly admissible filtered phi modulus. Of p-adic representations. So we define several functors and a category of p-adic representations over a local field. So the first functor is a de Rham functor. So they are all constructed using the general recipe of Fontaine, but using different period rings. So we will say that V is a de Rham representation if and only if it is B de Rham admissible. And in this case, we have an isomorphism between V tensor B de Rham over QP and G de Rham V tensor B de Rham over K. But if you know G de Rham, so we cannot reconstruct V from this isomorphism. So define decrease by the same procedure. So it takes values in the category of filtered modulus over K, phi modulus over K. Taking Galois invariance of a tensor product of V with decrease. And again, so we say that V is crystalline if and only if it is decrease admissible. Sorry? Okay, yeah, because I switched from French to English and vice versa. Okay. So from the general property of admissible representations, we Sorry? No, because because with our phi modulus over K0, but equipped with filtration over K, which is bigger, because they have an induced de Rham filtration. Yeah. Here we can recover V from decrease of V. Using sorry? Yeah? With QP. Using the fact that the invariance of field zero decrease under the action of Frobenius is QP. So if we take field zero and invariance under the action of Frobenius on the both sides, here decrease disappears and V is expressed in terms of this tensor product, so in terms of decrease.
You can recover only if it's crystalline.
I mean, here we can, here we cannot. There exists another case. The third and the last functor, D semi-stable. Which goes to the category of filtered modulus over filtered phi modulus over K, equipped with addition with a monodramy N. Which is defined by the same way, but using the ring B semi-stable. And it's easy to see that, again, we can recover semi-stable representations from their semi-stable modules. Okay. So here is a general picture. So what kind of representations appear in this theory and how they are related. So we have a category of crystalline representations, which is smaller than the category of semi-stable representations, which is smaller than the category of de Rham representations, which is smaller than the category of Hodge state representations, and which is smaller than the category of all p-adic representations. So just some comments it's easy to construct a p-adic representation which is not Hodge state. For example, taking a p-adic power of a cyclotomic character where A is not an integer. It is not Hodge state. So we see that this is a strict inclusion. It is easy to see that semi-stable representation, so this class is strictly smaller than the category of the RAM representations. So it can be easily constructed using representations, ramified representations with finite image. Give examples. So they are examples. So they are all the RAM automatically, but they are not semi-stable. So we checked this too. To give an example of semi-stable representation which is not crystalline, one should just imagine to construct a representation which is recovered by this special period x. So the semi-stable is obtained adjoining to decrease some spatial period x, which is the logarithm of this element. So one should construct a representation which is in some sense covered by, which has this element as a p-adic period. And such a representation, it's easy to construct. So let's define, so take Q, say a power of P times a unit, p-adic unit, and consider the action of the Galois group on roots, P and roots of Q. So this action is given by some map psi, yeah. And psi, so this is a map from GK to ZP. And we consider the Galois representation given by these matrices where chi is a cyclotomic character, and this representation is semi-stable but not crystalline. And such representations appear exactly in the semi-stable reduction of elliptic curves. So it is less obvious to construct how to construct a Hodge state representation which is not sorry. Yes, Hodge state representation which is not the RAM, and in fact, in the first paper of Fontaine about where he constructs the RAM and crystalline rings, he asks if one can find such an example. And so the entry is not obvious, but it follows from the fundamental exact sequence. So just I give this example and stop. So one can prove that any extension of the following form, 0, QP minus N, V, QP0, for N big or equal to 1, is not the RAM representation, but it is Hodge states. So this follows from the fundamental exact sequence and was probably written explicitly first in a paper of Bloch and Cato. With different period, with different weights. Yeah. Because if you have the same weight, you can construct something with upper triangular matrix, but here that's fine. Yeah. So I stop here.